Hey there, CHEN 308. Get ready for a high-stakes briefing. If you're tuning into this explainer, you're probably gearing up for Dr. Toyi's Oyegoka's Unit Operation 1 lecture tomorrow. Now, I know distillation can feel like this daunting labyrinth of phase diagrams and endless equations, but honestly, today, we're going to completely demystify it. We're taking those abstract concepts and turning them into a clear, intuitive blueprint, so you can walk into class tomorrow feeling totally prepared and way ahead of the curve. Let's get into it. Here is a quick look at our roadmap for today. We're going to start right inside the physical column itself, move through the McCabe-Thiele math, analyze our feed conditions, figure out how to optimize costs, and then finally wrap up with modern simulation and equipment sizing. All right, section 1, inside the distillation column. Because before we touch any math, we absolutely have to understand the physical layout of the equipment we're dealing with. But before we even crack open a textbook, let's take a second to remember why this actually matters in the real world. I mean, without distillation, we wouldn't have the gasoline in our cars, or frankly, half the stuff sitting in our medicine cabinets. It is literally the massive beating heart of industrial chemical separation. Whether you're working with petrochemicals, pharmaceuticals, or food processing, separating mixtures based on their different volatilities is the entire foundation of modern process engineering. When you picture those towering industrial complexes, you're basically looking at continuous countercurrent distillation doing its thing. Okay, let's virtually strip away the steel and look inside. Notice the feed stage right there in the middle, usually marked with an F. It divides the column perfectly. Up above the feed, you've got the rectifying section. This is where your more volatile component concentrates in the vapor as it shoots up toward the condenser. Down below the feed, that's your stripping section, where the less volatile component concentrates in the liquid as it falls back down toward the reboiler. Just keep in mind, every single calculation you do is going to depend on you understanding the difference between these two zones. And speaking of the top of the column, you need to lock this fundamental definition into your brain right now, the reflux ratio. It's defined as the ratio of the liquid returned to the column divided by the liquid removed as product. This isn't just some trivia question for a quiz, it is essentially the steering wheel for your entire operation. The exact amount of liquid you decide to pump back down directly dictates how pure your overhead product is going to be, and, equally important, how hard your reboiler has to work down at the bottom. So how do we actually keep track of all that vapor and liquid moving around? Well, that's where mass balance envelopes come in. By drawing these imaginary control envelopes over specific trays or over the whole feed stage, you establish your exact material and energy balances. You know the golden rule: what goes in must equal what comes out. So your total feed F has to equal your distillate D plus your bottoms B. By applying these envelopes, you can write out the internal mass balance equations for literally any tray in the system. Which brings us right to section 2, the McCabe-Thiele principle. We've got the physical layout down, so let's look at the ultimate mathematical cheat code for column design. If you want to design a column to hit a highly specific purity target using McCabe-Thiele, you have to systematically nail down these 6 elements. It's a step-by-step process. First, establish your rectifying operating line. Second, figure out your feed condition, which we call Q. Once you've got that, you can plot your Q line. Next, you find your required reflux ratio, which lets you plot the stripping operating line. And finally, you get to step off the number of theoretical stages. Honestly, if you skip or mess up a single step here, the whole design just falls apart. And this is where it all comes together beautifully. When you plot your mole fractions and draw your equilibrium curve, you can then map out all of those operating lines we just went over. You see that classic staircase pattern? That is you graphically stepping off the exact number of theoretical stages you need to reach your product purity. Think about how wild that is conceptually. We are literally using a bit of geometry on a piece of paper to engineer a massive chemical plant. Every single triangle on that graph represents one ideal tray where vapor and liquid reach perfect equilibrium. Moving on to section 3, analyzing feed conditions. Remember step 2 of the McCabe-Thiele method, determining Q? This is where a lot of students actually get tripped up. The thermal state of the feed entering your column completely changes the internal mass balance. It's not always just a basic liquid coming in. Sometimes that feed flashes into vapor right away, sending a surge of extra gas up into the rectifying section. Other times, it's a super cold liquid that actually condenses some of the rising vapor, sending extra liquid crashing down into the stripping section. Tracing exactly how those flow rates shift at the feed stage is absolutely critical. Do yourself a favor and keep this breakdown locked in your mind for the exam. There are exactly 5 distinct physical states your feed can be in. You've got subcooled liquid, liquid at the bubble point, a 2-phase mixture, vapor at the dew point, and superheated vapor. Each one of these unique states will physically shift the slope of your Q line on your McCabe-Thiele diagram, And that, in turn, drastically changes exactly where your operating lines are going to intersect. Let's shift gears for Section 4, optimizing distillation costs. Because look, as engineers, we aren't just doing math for fun, right? We're running a business. It is a massive balancing act. Designing a column is essentially a brutal tug-of-war. On one side, you've got your capital costs, the actual steel, the labor, building a taller column with more physical trays. On the other side, you've got operating costs, the daily, relentless expense of burning energy for reboiler heat and pumping coolant to maintain high reflux ratios. If you crank up your reflux ratio, you don't need to build as many physical stages. Awesome, you saved capital. But now you're skyrocketing the energy you have to burn every single day. So that brings us to this U-shaped curve, which is essentially your economic holy grail. It perfectly visualizes this trade-off. As your reflux ratio goes up, your annualized capital costs actually drop, but your annual operating costs start climbing linearly. When you stack those two together, you get that solid, sweeping curve up top, representing your total annual costs. When you hit the absolute lowest dip of that total cost curve, that is R-opt, your optimal reflux ratio. And that is exactly where you want your plant operating. Think about it. If you operate at minimum reflux, you'd mathematically need an infinite number of trays. Try pitching that construction budget. But if you operate at total reflux, you're producing zero product, which is a really fast way to get fired. Most real-world columns are designed to operate somewhere between 1.1 and 1.5 times the minimum reflux, just to safely hover right near this sweet spot. Finally, let's tie the whole room together with Section 5, simulation and equipment sizing. How do we take all these manual calculations into the modern workplace? When you eventually sit down to model this in a CAD application or a process simulator, the software doesn't just do the thinking for you. You have to feed it precise inputs. You need to tell it the column pressure, define your key components for both the top and bottom, specify the feed composition, and plug in the number of theoretical stages. And guess what? You only know what those numbers should be because you now know how to calculate them manually using the principles we just covered. Once you punch those parameters in, the simulator gets to work sizing the actual physical equipment. Take a second to appreciate that translation. It's turning your theoretical stages into physical steel tray designs, calculating the exact diameter you need so the column doesn't flood. It's scaling up the heat exchangers for your reboiler and condenser, making sure they can actually handle the massive vaporization and cooling loads demanded by whatever reflux ratio you picked. So here is the challenge I'm leaving you with today. Walk into Dr. Oegok's lecture tomorrow, not just ready to passively take notes, but ready to really engage. Ask exactly how these fundamental mass and energy balance equations we just explored bridge the gap into those advanced computer simulations. Ask how a manual step-off on a piece of paper directly dictates the diameter of the steel being built. Have an awesome class tomorrow, CHEN 308, and keep building that process engineering intuition.